section that I want to cover on recurrence relations is going to be using generating functions to solve recurrence relations. So we're going to be using generating functions with recurrence relations or recurrence equations. So to start this, what I want to do is give us a silly example where we really force generating functions in a somewhat unnatural way, but hopefully this will just show us how they relate, and then we can use that to extrapolate and use generating functions to do some more powerful things. So, as we've surely become so fond, let's try to find a function f mapping the naturals union 0 to the reals. And I want this function to satisfy f of 0 equals 1 and f of n plus 1 equals f of n. Now right off the bat, you should be able to tell exactly what the answer is. The answer is the constantly 1 function. That's correct. Good job. However, like I said, I want to really push this into the realm of generating functions and see how we can relate the two. So what I want to do is I want to say, and you might see the answer, see how this relates, but I want to just really elucidate this as much as possible. I want to say that whatever this answer is, I can think of f of n as a sequence. I can think of it as a sequence of, what are these outputs? Real numbers, a sequence of real numbers. And so I can consider a generating function, g of x, which is this sum, as and this time I'm going to use n just so that we're sticking to the variable of the f function. So n goes from 0 to infinity of f of n x to the n. So this is, like we said before, this is just another way to organize data. So this is just maybe a strange way, but it is a way to write down all of the outputs of the function f. So if this is my function f of n, g of x, and I want to somehow relate f of n to f of n plus 1. So let's just see what happens if I multiply g of x by x. Well, then I get x times the same series. N goes from 0 to infinity, f of n, x to the n. But watch what happens when I carry this multiplication through. This is the infinite sum as n goes from 0 to infinity, f of n times x to the n plus 1. Now, if I were to subtract g of x minus x g of x, and this derivation might be getting familiar, I'm going to have this sum, the sum of f of n x to the n, minus this sum, f of n x to the n plus 1. And man, that's not super helpful writing it that way. So I want to write out what happens. Well, what I'm going to have here, g of x minus x g of x, what I'm going to have here is f of 0 plus f of 1 times x to the 1 plus dot dot dot. And what I'm going to have over here, I'm subtracting off now f of 0 times x plus f of 1 times x squared plus dot dot dot. And what's going to happen? Well, I'm going to have f of 0 here, and let's look at powers of x. X has f of 1 minus f of 0. X squared is going to have f of 2 minus f of 1. But what do I know? That when I look at f of 1 minus f of 0, those are equal. When I look at f of 2 minus f of 1, those are equal. Which means on the right-hand side, I'm going to have just, so g of x minus x g of x. On the right-hand side, I'm going to be left with just f of 0. Because this is f of 0 plus, well, it's f1 minus f of 0 times x plus f of 2 minus f of 1 times x squared plus dot dot dot. But all of these go to 0 by my recurrence relation. Right? So I'm just left with g of x minus xg of x equals 1. And if this is starting to look familiar, good. I can factor out a g of x on this left-hand side. I guess I should have done that earlier. And I've got g of x times 1 minus x equals 1, which tells me I've got the generating function g of x equals 1 over 1 minus x. What do we know about this generating function? It generates the sequence of all 1s. We already knew the answer was going to be f of n equals 1, but this gives us a generating function way to say the answer is f of n equals 1. I guess this is the final answer. This generating function tells us that. Now, again, this relies on us knowing generating functions and knowing that this generating function generates the sequence of all 1s, but hopefully you see there is a relationship here. Okay, so if that was a little tenuous, sorry, let's now try to find a slightly more realistic application. And again, realistic in quotes, right? Let's try to find a function with f of 0 equals 0, with f of 1 equals 1. And what is my recurrence going to be? F of n plus 2 equals 2f of n plus 1 minus f of n. All right? So what I want to do here is I want to find a generating function, and then hopefully I'll be able to use that generating function to find a sequence. And that sequence will be, the nth term of that sequence will be the output of f of n. So I want to organize the data that I have about this generating function setup, kind of like I did last time, but I'm going to go a little bit more directly to what I'm looking for. I'm looking to relate the n plus 2 term, the n plus 1 term, and the n term. That is to say, I'm looking to relate 3 subsequent consecutive powers of x in my generating function. So I don't know what my generating function is, but it should satisfy g of x equals, so let's skip writing the infinite sum with the summation notation. Let's just write f of 0 plus f of 1 times x plus f of 2 times x squared plus dot dot dot. Maybe let me put in one more just for good measure. Let's put in f of 3x cubed plus dot dot dot. We've got room. Now let's look at x g of x, and this is going to be x times f of 0. Let me do f of 0 times x just to keep it looking nice. Well, yeah, let's do f of 0 times x plus f of 1 times x squared plus f of 2 times x cubed plus f of 3 times x to the 4th plus dot dot dot. And finally, let's do x squared times g of x is f of 0 times x squared plus f of 1 times x cubed plus f of 2 times x to the 4th plus f of 3 times x to the 5th plus dot dot dot. Now, I don't quite have the relationship that I want, because here I'm looking to relate the n plus 2 power to the 2 times the n plus 1 power and the nth power. So what I want to do is actually take this and multiply this equation by 2. So that, just qualitatively you can see I've got one coefficient of the nth term, one coefficient of the n plus 1 term, one coefficient of the n plus 2 term, but I really want 2 coefficients of this. So I'm going to multiply this equation by 2. This 2 is not as pretty. Let me clean that up a little bit. And that I just know that because I've got this 2 here. So I'm just preempting information that I'm going to want. And now I'm going to look for what I know about subsequent powers of x. Well, let's look at all of the squared powers. And let's look at all of the cubed powers. And what do we notice? We notice there's this relationship because I have f2 related to f1 related to f0. But I know that I have this relationship, f2 should equal 2 times f1 minus f0, right? So this should guide my intuition as to how I want to add and subtract these. So if I look at g of x, I want this to be positive, I want this to be negative, and I want this to be positive again, and then I'll have f2 minus 2 times f1 plus f0, or, you know, flipping it around like this. Let me write down what I'm saying. I want f2 to equal 2 times f1 minus f0. And another way to write that is I want f2 minus 2 times f1 plus f0 to equal 0, because that's really what this is saying. Yeah? So what does that mean? Well, that means that the coefficient on x squared in my information here should satisfy this relationship. Then, you know, if I take this relationship for, this was, you know, starting at n equals 0, with n equals 1, then I should have f1, 2, and 3 related in the same way by looking at coefficients of x cubed, etc. So I want all of those infinitely many coefficients when I add and subtract these in some way to go to 0. And how do I have to add and subtract them? Well, hopefully the pattern is becoming clear here. I want to look at x squared minus 2x plus 1 times g of x. Right? That's this guy minus this guy plus this guy. And what's this going to give me? Well, when I take g of x, when I take this whole line, subtract off this whole line, and add on this whole line, what do I get? Well, I'm going to get f of 0, because that term is on its own. Then I'm going to get plus f of 1 times x minus 2f of 0 times x, plus everything else in these infinitely many terms all become 0. Now what do I need to do? Well, I need to plug in what I know about f0 and f1. Well, what do I know? I have now that x squared minus 2x plus 1 times g of x is equal to, well, f0 is 0, plus f1 is 1 times x minus 2 times f0, so minus 0, minus 2 times 0, and this is a and then plus, you know, plus the big 0, plus the big nothing. Well, what does this tell me? This tells me, hopefully, that g of x is equal to x over x squared minus 2x plus 1. And if g of x is x over x squared plus minus 2x plus 1, this is x over x minus 1 quantity squared. And x minus 1 quantity squared, well, guess what? That is going to look a lot like x over 1 minus x quantity squared, because I've got this thing is squared. I can hit it with a negative on the inside. It doesn't affect anything. And what is this? Well, this is a right shift of a generating function that we know. The generating function g of x, if it was g of x was 1 minus x quantity squared, we know it would generate 1, 2, 3, 4, 5, etc. But now we're taking a right shift of that, which tells us that, you know, this generating function is a right shift. Let me write it down. It's a right shift of the sequence f of n is n plus 1. So if I've got f of n is n plus 1 and I'm shifting that to the right, that means my answer is going to be f of n equals just n. And you can check f of 0 is 0, f of 1 is 1. If we plug in now, what do we get? Well, f of 2 is going to be 2 times, oops, there's a shadow. F of 2 is going to be 2 times f of 1, which is 1. So 2 times 1 minus f of 0. So f of 2 is 2 times 1 minus 0. That's 2. Let's plug in 3 here. What's f of 3? Well, it's going to be 2 times 2, that's 4, minus 1. 3 is 4 minus 1. So that should hopefully convince you that our answer here is f of n equals n. All right. Now, if this was a little tenuous, I'm sorry. What I'd ask for you to do is go back and rewatch this, just trying to pay attention for why did I look to group those. So I'm looking to group these because I'm looking for the same power of x happening with subsequent terms in my sequence f of n. So I'm trying to relate the generating functions, which are allowing me to access infinite sequences, to this recurrence relation. So really the key here, like why did I write these three down, was because I was looking to relate three consecutive terms in my sequence. For a final example, I want to show the relationship between generating functions and recurrence relations by doing the same thing we did with the last one, but kind of backwards. So I want to start with the generating function, and I want to come up with a recurrence relation that describes the sequence that it's related to. So for example, let's find a recurrence relation associated to the generating function g of x equals 1 over 1 minus x squared. Okay, so what I want to do is basically run the same program that we ran for the last example, but backwards. So in order to get our heads wrapped around this, what I'm saying is I want to take this generating function, which is 1 over 1 minus x squared, which is this generating function g of x, and it should have, it should be a sum as n goes from 0 to infinity, it should have coefficients which are going to be f of n's for some sequence, and I want to find a recurrence relation that defines this sequence. So let's write down what we know. Well, if we take this part of the equation and just multiply it out, what we're going to get is g of x minus x g of x minus x squared g of x equals 1. So let's write this out as best we can. So just multiplying both sides by that polynomial on the bottom. So let's write out what we get. Well, g of x is going to be, of course, f0 plus f1 times x plus f2 times x squared plus dot dot dot. X g of x is going to be f0 times x plus f1 times x squared plus f2 times x cubed plus dot dot dot. And finally, x squared times g of x is going to be f0 times x squared plus f1 times x cubed plus f2 times x to the fourth plus dot dot dot. Now what I want to do is somehow add and subtract these in such a way to get just 1 to pop out. So let's shift things around, and let's look at the coefficients of the subsequent powers of x. So we've got the linear term, constant term, quadratic term, etc., going on and up, etc. And this should give us some information. Well, what's the information that it gives us? Well, when I add and subtract these like this, what am I getting? Well, I'm getting 1 equals, so this is just sort of scratch work in between here. 1 equals g of x is going to be f0 plus f1x. Well, hold on. Let's do the subsequent powers of x. So f0 is on its own. Now what do I have for x? Well, I've got g of x minus xg of x. So this is going to be f1 minus f0 is x, because remember I've got g of x minus this minus this. What's going to be my quadratic term for x? So plus, well, I've got f2 minus f1 minus f0. f2 minus f1 minus f0 gives me my quadratic term in x, etc., etc. And then the subsequent terms, I guess let me write out, the nth term will look like f of n minus f of n minus 1 minus f of n minus 2 x to the n. But what do I have on the left-hand side here? I've only got a 1. Well, this 1 is a constant term. There's no x on this left-hand side, which tells me f of 0 is equal to 1. I get that because that's the constant term. Okay? Now, what's my linear term? Well, I have that f1 minus f0 is how many x's I have. Well, I have 0 x's over here, so this is equal to 0. But I can plug in what I know about f of 0, and I get that f of 1 minus 1 is equal to 0, which means f of 1 is equal to 1. Finally, and for the last piece, I need that each of these higher powers of x have a coefficient of 0, which means I need f2 minus f1 minus f0 to be 0, etc., etc., etc. That means what I need in general is fn minus fn minus 1 minus fn minus 2 should be 0. So I have that f of n minus fn minus 1 minus fn minus 2 should be 0. Well, if I put all of this together, I have one initial condition, two initial conditions, and a recurrence relation. And what is this recurrence relation? Of course, this is f of 0 equals f of 1 equals 1, and f of n equals f of n minus 1 plus f of n minus 2. And we end where we began. This is exactly the Fibonacci sequence.